Good afternoon. Can we hear me? Okay. What I'm going to talk about now is the description of some monitoring devices able to detect the cardiopulmonary activity, which can be integrated in wearable systems through radiant sensing. This slide is of course, is not an exhaustive picture of all devices which are able to detect the cardiopulmonary activity, but basically gives an idea of the what are on this scenario. And the device go from commercial devices such as echocardiographs or spirometers, frequently portable, but basically it cannot be integrated in wearable systems. And then we have the integrated system, which acquire multiple physiological signals such as life shirt, smart shirt, and also we have the product which are the outcomes of European projects such as Wealthy, MyHeart, Protex. Wealthy and MyHeart are already over, and the Protex is currently running within the 6 framework program. Here I will describe two different monitoring systems. The first one is based on ultrasound technology, and the second on radio frequency technology. The first system is characterized by a special transducer which has specific properties of having a low Q factor, which implies a wide bandwidth, and this allows us to use this transducer at low and high frequency. So we can drive the transducer in order for it to work as a simple microphone, simple piezoelectric transducer, in order to detect the sounds coming from the heart and breathing signals and heartbeat. And it can be also by a suitable switch. It can be used at high frequency. It can be excited in order to generate an ultrasound wave, an ultrasound signals, in order to investigate the internal organ of human body. The second system is based on radio frequency technology. The ultra-wideband radar is an innovative technology, and I will describe more in detail after. And it is comprised of a system of module which includes the transmitter and the receiver, and by means of an antenna, the signal, the electromagnetic signal, is electromagnetic pulse is generated, is emitted by the transmitter and received and afterwards processed. In order to get a complete picture, or an exhaustive picture of the cardiopulmonary activity, we have to acquire several physiological signals. The most widespread signals acquired for having to have the status or the activity of the cardiac activity is the ECG, acquired by simple ECG electrodes. But this signal is referred only to the electrical activity of the heart. But we have the mechanical behavior of the heart can be acquired by means of the heart, for example, the heart wall movements, or the heartbeat, or the heart sounds. In addition to the breathing signals, can be acquired by the system I introduced before, and I will describe hereinafter more in detail. The first system, the ultrasound-based transducer, is comprised of a piezoelectric element, which is a copolymer PVDF. This piezoelectric element has a low Q coefficient, which implies a large frequency bandwidth, and this allows us to use this transducer at low and high frequency response. At low frequency investigation, we can use this transducer such as simple microphone for detecting specific heart sounds, and at high frequency we use this transducer to detect the heart wall motion, heart wall movement. As for the low frequency analysis, we need the specific requirements related to the eye sensor. So the sensor we use should be very sensitive, because the signals coming from the inner body are very low. Sensor positioning is a very crucial aspect to be addressed, because the intensity of sound sources changes on the position of the transducer. And then the careful processing of signals has to be done, a pre- and post-processing, in order to extract significant information and parameters related to the behavior, the heart behavior. One aspect of the low frequency analysis is the detection of tones. So tones are sounds coming from the heart, and these tones can be classified basically in 4 different classes. Each tones can be associated to a specific events of the cardiac cycle. For example, the first tone coincides with the beginning of the left ventricular contraction, followed by the closure of mitral valves, and so on. When the transducer is used at a low frequency, it works such a microphone, and it can detect these tones. In addition to tones, this transducer is able to acquire this type of signals. This is an example of signals acquired by the transducer. This is the heartbeat. This is an overlapping of the heartbeat with the breathing signals. In order to assess, to validate, so this is a preliminary assessment, of course. I'm sorry. Each peak is overlapped on the breathing signals, corresponds to each ECG QRS complex of the ECG signal, and the ECG signal was acquired simultaneously in order to verify if the signals acquired by the transducer was reliable. Of course, if we have this kind of signal, so we have 2 different components, 2 different information at 2 different frequency range. And this is very important, because we can separate the 2 information in order to discriminate these 2 kinds of information, the breathing signals and the heartbeat, by applying very selective filters. In this case, we applied the low pass Butterworth filter, a pass band Butterworth filter. This is the frequency